This is the talk by Kostya Drach from, I think, Austria or Marseille, I don't know, maybe
Austria.
both. Okay, now from Vienna, yes?
Yes.
And he will tell us how to use box mappings as black boxes.
Okay, thank you very much. It's my pleasure to be in band level, albeit virtually. And thank you, the organizers, for inviting me to give this talk. My apologies to those who've been to the previous week in Marseille, since there will be a big overlap in what I will be talking today. But let me start. So today I want to sell you a box full of useful tools. And I want to convince you that once you master this box, you are able to solve many of the hard rigidity questions in one-dimensional complex dynamics, sort of without going into hard machinery that have been developed until recently. This is a joint work with several people, Trevor Clark, Oleg Kozlovski, Dierk, Schleicher, and Sebastian from Strien. Let me start with the picture that's probably familiar to many of you. And this is a picture of a particular parameter plane for a rational map. And for those who recognize the picture, this is a parameter plane for degree 3 cubic Newton map. And here you can see a small Mandelbrot set embedded in this parameters plane. And the question, of course, what is the mechanism why this Mandelbrot sets appear in this parameter space? And the answer is, of course, in the dynamical plane, which you can see on the right. And in this dynamical plane, we can have a critical point. And it so happens that if we take some disk around this critical point and iterate it one time with our map F, we'll get some other disk. And then if we iterate one more time, it will return around our starting critical point C with a slightly larger size. And we can notice in this situation that C, as well as all its even iterates, will be contained in this smaller disk. In this case, I can forget about the whole ambient dynamics and consider just the second iterate of my map restricted to this small disk that I started with. And in this way, I obtain an induced dynamical system that essentially captures the critical orbit of C. And with that respect, if I want to study the critical orbit, it is enough for me to look at this induced map. And of course, this is again well known to many of you. This is a notion. In this way, we arrive to a classical polynomial-like maps. Let me remind you that a polynomial-like map is a proper holomorphic map between two open disks U and V with Jordan boundaries, such that the closure of U is contained in V. So we have some branch covering from a smaller disk to a larger disk. And for such object partially defined maps, we can define a set on which we can iterate our map infinitely often. And this is defined as the intersection of all the preimages of V. And it's called a filled Julia set of F. And the celebrated straightening theorem due to Duady and Hubbard tells us that every polynomial-like map of degree D is hybrid conjugate to some polynomial, some actual complex polynomial of degree D. And moreover, if the filled Julia set is connected, then this P is unique up to affine conjugation. Of course, the question is, if this is so, if we can extract a polynomial-like map from our embedded dynamical system, then the map is called renormalizable. Additionally, we should require that the filled Julia set for this renormalization is connected. This is a proper way. Otherwise, our map is non-renormalizable. And of course, the question is how to construct a more sophisticated induced dynamical system which might include more critical orbits or critical points if we are dealing not with a unique critical situation, but with the presence of several critical points. And the answer is to consider first return maps to nice sets. Let me remind you what is a nice set. And in this sentence, it's not just an adjective, it's actually a mathematical term and is due to Markov-Martens. And we say that for a map F from U to V, some set B is nice if the forward orbit of the boundary of B does not intersect the interior of B. And if we assume that our set B is nice, for instance, it contains four topological disks on this picture, then we can define so-called first return map. How it is done? Well, we start with picking some point Z and assume that after, say, 3 iterates, our point returns to the set B. So, for instance, we have this situation. So we can consider third iterate of our map going from Z to its image. And if I denote this disk as V, I can pull back this V under this third iterate to some set. And the question, how should I draw it? For instance, suppose that the pullback looks like this. And well, now we can analyze. And in fact, notice that if, for instance, I pick a point here, then say W, then this point W after 3 iterates will land somewhere here, which is explicitly prohibited by the definition of my nice set, because this boundary point is mapped to the interior. Therefore, this particular pullback is impossible, and therefore this picture is wrong, and I should have drawn it differently. You can convince yourself that the pullback cannot be larger, and the only possible situation in which this is all well defined is if the pullback looks like so. And of course, if Z is mapped to this set V here under the third iterate, in the same way, all points in this pullback will be mapped under the third iterate. And in this way, we obtain what is called a branch of the first return map. To B. And first stands here because we picked this 3 as being the first time under which the orbit of Z landed in B. And in this way, we can consider all possible branches of our first return maps to this set B. And of course, the combinatorics of these branches can be quite wild. So we can have many branches that map somehow in various directions. We can have components of B that are mapped over some other components of B, and so on and so forth. So I can draw any combinatorics, and in theory, I can cook up a map that has this particular type of first return maps. And moreover, I can have infinitely many components. It's not necessarily finitely. If you think about, for instance, a situation when the critical orbit is dense in the Julia set, then if you take some disk and suppose it is a nice disk around the critical point, then the first return map to this disk will necessarily have infinitely many components. And notice that if some F orbit of a point Z intersects B infinitely often, for example, the point Z is recurrent, then the first return map will be defined for infinitely many iterates of Z. And with that respect, this first return map essentially sees the whole orbit. So we skip some steps in the orbit of Z, but in principle, we understand long-term behavior of this point Z. And therefore, this is a very useful concept how to analyze orbits of our dynamical system. if we are careful so that we pick B so that it contains the critical set of our map, then it's not. It's easy to see that the critical points of F will be the critical points of the first return map, so that we do not create any additional critical points. And moreover, with some luck, we can arrange so that the mains of the first return map that I drew here indeed compactly contained. So I have some space between components of the first return map and our starting set. And with that respect, with this procedure, we arrive to a structure of so-called complex box mapping. Let me now give you a formal definition. For us, a complex box mapping will be a holomorphic map from U to V between some open sets curly U and curly V, for which the following four properties are satisfied. First, F has finitely many critical points. This is, of course, something that is much easier to work with. And if we study rational dynamics, then we have infinitely many points to start with. V is a union of finitely many open Jordan disks. And here I want to emphasize that our range is the union of finitely many open disks. Then the restriction from any component U of curly U to its image is a proper map, some branch covering or univalent map. And finally, every component V of, so if I pick any component V of curly V, and if I pick a component from U, then they either do not intersect or they coincide, like in this situation, or this component of U is compactly contained in the component of V. What I was describing so far in long sentences and long words actually describe you this picture. This is exactly what we want to formalize, and this is an example of a complex box mapping. So this is the structure, and the structure appears naturally as a first return map to some union of nice sets. And therefore, our goal is to understand what are the properties of such general objects and what conclusions we can draw from those properties. But before moving on, let me give you some further definitions that are associated to the notion. In fact, this structure of starting nice sets, when we pull them back, defines us in some sense a puzzle partition. So a puzzle piece for our box mapping is a connected component of the nth image of our set V. And n here is a measure of depth for a puzzle piece. And once I have puzzle pieces, I can intersect all of them. And with that, I will arrive to the notion of a filled Julia set. Again, as with polynomial-like maps, this is a set on which I can iterate my map infinitely often. And another useful concept is of fiber. For that, if P sub n of x is a puzzle piece of depth n containing some point x in the filled Julia set, then the fiber of x is the intersection of all puzzle pieces containing my point x. This is a very useful object to think about because it has a lot of proper dynamical interpretations. First, we say that the fiber is trivial if this fiber consists of point x itself. And if we think about these puzzle pieces of various depth as some sort of symbolic dynamics on our space that is given by a box mapping, then the fiber of x is a set of points with the same itinerary through the puzzle partition. In other words, a fiber is a set of points that travel together when we iterate them by our box mapping. And if the fiber of point x is trivial, then we can say that in fact we can distinguish combinatorially the orbit of x among all other orbits of our box mapping. So that it has a unique way of traveling through the puzzle pieces. And as again, maybe many of you know, this is the proper dynamical way of looking at the questions of local connectivity. But we will return to that a little bit later. And here's an example of a box mapping. And this is a fairly simple example, and this example illustrates that this notion was some sort of implicit even in the early works of Fatou, and of course was much more developed in the work of Hubbard and Brunner. This is an example of a cubic polynomial with two critical points, -1 and 1. 1 is escaping critical point, and -1 is not. And if we take some large equipotential around two critical points and pull it back, we'll have two connected components, one here in orange and another here in orange. And I call this U1 and U2. And now if I take the union of U1 and U2 and restrict my polynomial to these two, then I arrive to a complex box mapping. A map from this disk to this yellow one, and from this disk again to yellow one. The first branch is 2 to 1, the second branch is 1 to 1. And of course, here, if we look carefully, then this black part is exactly a fiber of -1. And you can also see here different shades of orange, which resembles various depth of puzzle pieces, right here and here, and so forth. But of course, this notion of box mapping is a long history, and let me try to account for some of the episodes. And of course, since it's very intuitive notion when you know it, it has a complicated history. In real interval dynamics, similar construction was first appeared in the works of Jacobson and later Guggenheimer and Johnson, who actually coined the term box map. And here you can see a picture which I took from their paper, and this is exactly why in real world it was called box mapping. In fact, it was constructed as sort of an inducing scheme for various smaller intervals. And we have the nest of these boxes that provides kind of finer and finer partition. For these intervals, we define smaller and smaller branches. And in some versions of this inducing scheme, these branches were required to be all univalent or monotone in this setup. And of course, later on, it was prominent in the work of Grachuk and Schwantek, and then Nowitzki and Van Strien, and probably many others, which I apologize to if I didn't mention some names. But of course, there was a side of the history from a holomorphic dynamics point of view. And in the early 90s, Misha Lubitsch introduced the notion of generalized polynomial-like map. And this is a complex box mapping where V just consists of one component and U of only finitely many components. And this is this notion of generalized polynomial-like map, as opposed to this inducing idea, was simulated in Lubitsch's work by ideas coming from renormalization. In other words, considering first return maps to a certain set plus rescalings. And this idea of renormalization later on appeared to be extremely fruitful and helped to tackle many questions in homomorphic dynamics as well as in real dynamics. And in other works, you can find other avatars to this concept. Some people call it puzzle mapping, some people call it R mappings. But let me emphasize that for us, our box mappings are generalized renormalizations in the sense of Lubitsch. So we adopt this point of view that it is useful to look at first return maps and, if need be, to do some rescannings. Okay, but what can we say about general box mappings? Well, in fact, if you look carefully at this definition, you can find out that it's extremely general. And therefore, it allows for some pathologies that one would not expect when dealing with rational maps. And in the joint work with Trevor, Oleg, and Sebastian, we cooked up some of the pathologies that one should not expect from something that is extracted from globally defined dynamical system. In particular, we constructed a box map in F1 such that the filled in Julia set is the whole is equal to U and V. And this is a that simple box mapping when you take just the unit disk as equal to U and V, and your map is just an identity. Formally speaking, it is a box mapping, but it's extremely boring one. Another example we cooked up is a box map in F2 that for which the non-escaping set has full Lebesgue measure in the domain. There's empty interior, and there exists a positive measure set of points that do not accumulate at any critical point. And this is something that you would not expect, because usually if a set of points do not accumulate at any critical point, then you would expect some sort of expansion, and you can probably convince yourself that this is some sort of a hyperbolic set, which then has zero Lebesgue measure. But this is not the case. And this is exactly the mechanism precisely because we allow for infinitely many components in the domain of our map. Another example one can construct is a box mapping with a wandering disk, which means that it's not necessarily that puzzle pieces that you can define, they shrink to points. And finally, we're able to construct an example of a box mapping such that the set of points that in the filled Julia set whose orbit converts to the boundary of the range has full measure. And well, on the first hand, it's not clear why it is a pathology. But if you think about, if you know, and I will mention it a little bit later, if you know about Yoccoz puzzle pieces, that the construction of those puzzle pieces is done in such a way that the boundaries of puzzle pieces are repelling in some sense. And therefore, it's very unlikely, and in polynomial case, in many rational case, you can prove that this set of points that actually converge to the boundary should have zero measure. But again, in this general setup for general box mapping without any additional knowledge, we can look up such pathological examples. And therefore, if we want to conclude something meaningful and having some applications in mind, we arrive to the notion of dynamically natural box mappings. And we call a box mapping F dynamically natural if, in some sense, all these pathologies do not occur. And informally, we say that a dynamically natural if, first of all, every component of U has escaping points. Secondly, the Lebesgue measure of points in the non-escaping set that do not accumulate at any critical fiber is zero. So this is something that we would expect for rational maps. And finally, the filled Julia set consists of points whose orbits from time to time visit components of U that are well inside of V. This is a slightly technical assumption, which says that for any point X in the non-escaping set, there exists some delta that depends on this point, such that and exist infinitely many components Ui and Vi of U and V, such that the modulus between Vi and Ui is at least delta, and the orbit of X intersects Ui, so that we indeed have this situation, if this is UI, this is VI, we have some space here, and our orbit indeed travels and jumps from time to time to such UIs. If you think about it, it's extremely weak.
So does this assume that there are infinitely many components of U?
Well, if we have finitely many components, this is automatic, right? If we have finitely many components, this is automatic, and if we have infinitely components, then that's to be assumed.
I see. Okay.
Mm-hmm. Okay, but we're with this notion, we can say that map F is box renormalizable if there exists a nice union V of topological disks, well, in the domain of definition of F, so that the first return map to V under F is dynamically natural box mapping, and such that the critical set of F of capital F is inside the critical set of small f. So we formalize it, right? Same way as we said that a map is renormalizable, we can extract a polynomial-like map. Here we want to extract a box mapping, and this particular additional property says that we do not want to produce additional critical points, right? Because you can imagine a situation if, for instance, we have some disk, say V, and we consider, and it's so small, so we consider first return map to this V, and all these components that I drew, they sort of pass through a critical point. So their orbit goes something like this before they return to V, and so on. And of course, that would generate in all these components a critical point. We do not want this. So we do not want to create additional critical points. Therefore, we put this assumption. And this assumption will be usually satisfied by choosing this curly V to contain the critical set of small f from the beginning. Okay, a couple of remarks. A box renormalizable map may or may not be renormalizable. And this is a notion, box mapping F with a recurrent critical point is actually infinitely many times box renormalizable. And this is essentially follows the motivation and ideas from Lubitsch from the early 90s, which says that we can be non-renormalizable in the sense of Duady and Hubbard, but we can be infinitely many times renormalizable in this generalized sense. And how do you do that? Well, if, for instance, you have a box mapping, or for example, let me draw some simple combinatoric like this, and we have two critical points, and if they are all recurrent, what we can do, we can just take the components containing these critical points, say U1 and U2, and consider a first return map under my starting box mapping F to this union U1, union U2. And this first return map will be again a new box mapping, and so forth. So we can keep taking first returns to to critical neighborhoods that will produce us an infinite sequence of maps. And with that respect, our starting map is infinitely many times box normalizable. Okay, and it is actually not clear that if we start with a globally defined F, say rational map, how to understand whether it's box normalizable or not. And let me give you an intermediate takeaway. If for some reason we know that it's box normalizable, I want to convince you that we are in business. And if we are box normalizable, then we can use the black box that I will describe you momentarily to conclude rigidity results. Therefore, kind of with this set of techniques, it is enough to understand whether we are box renormalizable. Okay, but what are the results in the box? First of this result is what we call dynamical rigidity for box mappings, and it says the following. It says that if F is a dynamically natural box mapping and I pick any point in the non-escaping set, then either Z has trivial fiber, which means that I can distinguish combinatorially with respect to partial partition of box mapping the orbit of Z, or we are in a normalizable case and Z belongs to or is mapped to by some finite iterate to the filled Julia set of some renormalizable dynamics. So this theorem says that in this world, we have two alternatives. Either we understand completely what's going on, or we are dealing with a polynomial-like map, and hence we can use a lot of knowledge that we know so far about polynomials. So this is a theorem due to Dierk, Schleicher, and myself, which is a generalization of much more non-trivial result of Oleg Kozlovski and Sebastian van Strien, and who proved it for when they were working with multi-critical polynomials. And their approach was, again, very, very involved. It used the enhanced nest construction, which is a combinatorial tool how to understand recurrence of critical orbits due to Kozlovski, Shen, and van Strien. And they used analytic tool, which is a covering lemma due to Jeremy Kahn and Misha Lubitsch, who showed, together with Artur Avila and Vexao Shen, how to use this, this analytic tool to prove rigidity in the unicritical situation. So these tools together, this is actually what is under the cover of this dynamical rigidity. Well, in particular, if all fibers in the Julias, if we're in a non-renormalizable situation for our dynamically natural box mapping, then all fibers are trivial. So if we know for some reasons that we are non-renormalizable, then we know that we are trivial. The next tool that we have in our toolbox is some ergodicity properties of non-normalizable dynamically natural box mappings. And this tool says that for non-normalizable dynamically natural box mapping, for each ergodic component of F, there exists one or more critical points such that they are Lebesgue density points of this component. So we have a very tight connection between each ergodic component of our map and critical points. In particular, the number of ergodic components is bounded by the cardinality of the critical set. The next toolbox, the next result in our toolbox is results about line fields. Line fields is a simple concept that says that if I have a line field, a measurable line field is assignment of lines through every point Z in the non-escaping set, such that it is preserved by the dynamics. So if I look at the image of my point Z, then the differential maps the lines through that to the lines through F of Z. And these line fields, they are naturally spaces of QC deformation for our maps. And since they're supported on K of F, it means that they only make sense if K of F has some positive measure. And we were able to show that for non-normalizable dynamically natural box mappings, the map F carries an invariant line field only in a very, very particular situation for the map. And in particular, so this is a formal statement, which I'll probably skip since I'm a little bit running out of time. In particular, if we are in sort of Yoccoz situation and each puzzle piece contains an open set of escaping points, then F carries no invariant line fields, and hence does not admit spaces for this QC deformation. In fact, we defined what's called lattice box mappings. These are class of maps for which indeed these line fields can be constructed, invariant line fields. And well, they do exist, as for instance, this beautiful picture shows, but let me again skip this part. Final result in our toolbox is parameter rigidity, or just rigidity. And this is the result of the following kind. Again, we start with two non-normalizable dynamically natural box mappings, F and F tilde. And we assume that there exists some starting QC homeomorphism that sends, well, V to V tilde and U to U tilde. It is a conjugacy on the boundary of U. And additionally, it is combinatoric F tilde, combinatorially equivalent to F with respect to this H. Let me briefly explain what does it mean. On the picture here at the bottom, you can see two box mappings, well, actually F and F tilde. And I can encode all the preimages, all the puzzle pieces by their itineraries, of course, and also by some homotopy information by connecting puzzle pieces of various generation to the starting puzzle piece by some curves and taking preimages. So this picture contains puzzle pieces of depth 0, 1, and 2. And you can consider itineraries and some homotopy information, how these puzzle pieces are connected. And if this information is preserved by H, this is what we call combinatorial equivalence with respect to H. Right, so in simple terms, it means that we assume that our box mappings are combinatorially, they have similarly, exactly the same. And under these assumptions, we conclude that F and F tilde are quasi-conformally conjugate. Well, and in fact, this conjugation agrees with H on this fundamental domain. So this is a typical result about quasi-conformal rigidity when we promote combinatorial equivalence to something stronger, or topological equivalence to something stronger, which is a QC rigidity. And again, this is an involved result, which uses a lot of machinery that was developed previously. Again, this enhanced nest construction, covering lemma, and there's an additional analytic tool about quasi-conformal maps called QC criterion. Okay, so that was our toolbox. And now the question, how do we apply it? And this is a simple-minded strategy how to apply this toolbox. Just very simple. It consists of 3 steps. And after these steps, you are sort of a winner if you can do all of them. So first step is that you have to establish, starting with your map F, you have to establish whether it's box normalizable or not in some non-trivial way. For example, if we can construct some nice neighborhoods of a critical set that intersect the Julia set, then we can take a first return map, and then we have to check, and then we can take this first return. Then we check whether the resultant first return map F is dynamically natural. And if we are successful in steps 1 and 2, then we actually do not have to redo all the machinery. So we do not have to uncover what is beyond all these nice and deep results, and just embed the existing rigidity results for such f's back into the dynamics of small f. So this is in fact the actually a nice strategy, and in fact it works. In many scenarios, it actually works. And let me skip through some slides to arrive to a final list of examples where the strategy actually works. So first set of these examples here consists of rational maps with totally invariant, infinitely connected for two component. And this is an example where you can construct box mappings sort of in a sense of Brunner and Hubbard using this fully invariant, infinitely connected two components. And once it is done, you can use this black box machinery to conclude the results. And the citations I gave here, these are by authors who first proved this, but some of them were not using this type of machinery. But you can, in fact, redo all of their proofs in a unified way. And you conclude this Brunner-Hubbard conjecture, absence of random line fields, and ergodicity. Another set of examples in this scenario, but of course, historically, it's all where it all started, is a set of non-normalizable polynomials of arbitrary degree, but without neutral periodic points. In this situation, we can use the standard Yoccoz construction of puzzle pieces. And let me show you this slide. I'm sure it's familiar to many of you. We take some periodic rays landing at the same point. We take an exponential for our polynomial. And this is our starting partition. We start to pull it back using the invariance of these rays. They create finer and finer subdivision of the Julia set into regions which are puzzle pieces by definition. And all of these sets are nice. And with this respect, we can select necessary puzzle pieces and take first returns and arrive to a structural complex box mapping. And with that strategy, quasi-conformal rigidity, absence of errant line fields, and triviality of fibers was first proved by Avila, Khan, Lubitsch, and Shen in the unicritical case, and then it was proved by Kozlovski and von Strien in the multi-critical case. Another set of example is the result due to Roche and Yin, which proved that the boundaries of for two components of bounded for two components of polynomials of arbitrary degrees, which are not Siegel disks, they are locally connected. And this is the situation where construction of puzzle pieces is a little bit different. And in fact, what one can do, if this is what I drew is as a for two component, one can take lending external rays, periodic rays, co-lending internal periodic rays, and we can crop this whole picture with internal equipotential and external equipotential. And with that, we arrive to these sets, which partitions the boundary of the for two component. And this is the puzzle pieces that they defined. And using this puzzle partition, you can again select some finer preimages of those, take this union and consider first return map, and that will produce you a box mapping. And after that, you can conclude using dynamical rigidity that in fact, using the fact that the fibers are trivial at this point, so you can conclude that the boundary is locally connected. Another set of example is so-called McMullen maps. And these are the maps of the form that, as you can see on the slide. And Qui, and Yin prove that the bound, so infinity for these maps is an attracting fixed point, and they prove that the boundary of infinity is locally connected. And this is the situation already as a rational map, one-dimensional family of rational maps. And they use the symmetries of this map to construct some sort of cut-in race through the Julia set and arrive to puzzle pieces. So in that respect, they successfully accomplished step one. One can check that you can do step two, and hence you can do step three and use this black box machinery to reprove their result without actually redoing much. And finally, the final set of examples. This is probably the largest family of rational maps for which we know the rigidity results so far, and this is so-called Newton maps of polynomials. And let me, in the last 2 minutes or so, flash a couple of slides just to explain that we were able to successfully do step one for Newton maps, and hence steps 2 and 3, and hence conclude the rigidity results. So step one is to construct puzzle pieces. And for Newton maps, we have a very particular structure. So this is a dynamical plane of a Newton map, and these big colorful regions are precisely points where this map, which is defined as a root finder for a certain polynomial, these are the places where points converge to particular roots. And as you can see here, they all nicely touch at infinity. And this particular structure of touching at infinity allowed us to use an internal coordinates for these basins to take fixed rays within the basins. This is another picture, and take their preimages, successive preimages. Of course, this is a rational map. There are problems since we have poles, we have points like here that maps to infinity, and therefore preimages of fixed rays, they're not necessarily connected to the starting set of rays. But in fact, this problem can be overcome. We show that if we, with Zhenya Mikulich, Johannes Ruckert, and Dierk Schleicher, we show that, in fact, if you pull sufficiently long, you can catch all the poles, and with that respect, sort of construct this graph with proper, which is forward invariant, and the complement of this graph, each complement is simply connected. And in that respect, we arrive to a notion of Newton puzzle pieces. And on the slide here, you can see an example of a Newton puzzle piece. So this is again a concatenation of some equipotentials within the root basins and some pieces of preimages of those fixed rays within the immediate basins of roots. And again, this is a renormalizable situation. You can imagine here a map that maps this puzzle piece over this puzzle piece with some degree. And with that respect, we were able to analyze the situation further and further. And I skipped, unfortunately, I have to skip a couple of slides that explains that, in fact, we can do step 2, which means that the first return maps to a properly defined union of Newton puzzle pieces indeed produces for us dynamic natural box mapping. For that, you have to establish so-called triality of fibers at infinity. But if we have this, then we actually can harvest now. And the result, and this is an example how this black box mapping machinery works, is the following theorem. And as you will see momentarily, just a translation of what I was speaking about box mappings. So we can show that for arbitrary Newton map, we have either point convergent to a root as it should, or the orbit is uniquely distinguished. We have triality of fiber, and or this point that maps to some normalizable dynamics. And the same way we can prove parameter rigidity, which says that we can promote combinatorial rigidity of Newton maps to quasi-conformal rigidity and affine rigidity. And this is an example how this machinery actually can be applicable. And I think I'm running out of time, so I thank you for your attention.
Thank you very much. Some questions? From online participants? Okay, if not, then let's thank the speaker again.
Thank you.
And also for all the speakers of today's session. And this is the end for today. Now it's dinner and we start tomorrow at 9 as usual.